Good afternoon. Quick reminder for you to all be here in this room at 4:30 this afternoon for the grand prize giveaway. There's some really cool stuff there, Raspberry Pis, YubiKeys. And I believe there's a rumor that there might even be a couple of DevConf hoodies in the prize pool, which seem to be the most popular item. I would like to now move on with the next talk and introduce Ralph Bean once again today. Thank you.
Thank you. So I think this talk is going to be more of an odd duck than I'd originally expected when I submitted it to the conference, in that it's talking about microservices, and there have been other microservices talks at the conference, but the majority of them have been focused on the aspects of infrastructure that go into supporting that mode of development, whereas this talk is going to be about the actual process and applications development of building services and the microservices and some of the problems that come with that and why you might want to do it. Some of that has also been talked about in the JBoss track, but this is not related to JBoss. This is based out of the experience of the Fedora Infrastructure team. And we build the majority of our services in Python. So there's some similarities there, but also some differences. Oops. So let's talk about technical debt first. So what is technical debt? It's this new financial instrument where you take all kinds of different technical problems and then you recombine them into like a mortgage-backed derivative. No, that's not technical debt, right? We're talking instead about bad decisions is really what technical debt comes down to. Bad decisions that end up causing you to pay more down the line than you had to up front, which is right the same way that financial debt works, is that you pay more over time than you'd originally gotten out of it. And what that looks like in practice when you're writing code usually comes out in terms of code smells, if people are familiar with the term. They're not things that are bugs or things that are actually broken about the software, but there's some things about the software that as you're writing it or reading it and working on it, smell bad about the code. So duplicated code in particular is something that we see a lot in our services. I have some examples up here if people are familiar with it, but we have the Fedora account system, and we have all these services across our infrastructure, and all of them need to cache that data. But something, just because we've been lazy along the way, is we just rewrote the mechanism to cache fast data in every one of these places. And so now whenever that changes, we have problems that we have to go and fix it in all the places and do more work than we did in the beginning when we were just hastily copying code. Long methods and large classes are things that, when you're reading code and you think, oh, this is concise, and readable, and then you get to that one function that goes on for 27 pages and you think, what is this, what does this even do? Contrived complexity. Oftentimes you'll have someone who thinks that they're a very, very intelligent programmer and they want to demonstrate that and immortalize that in their code, and so they take what could otherwise be a simple problem and then invent this really convoluted way of solving it to really maximize their use of functional programming or something like that. So that can be a problem. Places where there are half-implemented features where you got somewhere but you didn't finish it, that causes so many problems later on because a new reader of the code encounters that and then thinks, what did this even do? Am I breaking this? Well, it didn't work when they got there, but they don't know that yet because it's only half implemented. So it causes lots of confusion and delay. No or poor documentation, commented out code, having tests that, having a project that doesn't have any automated test suite, or sometimes even worse, having a program that does have tests, but they're constantly in a state of being broken, creates a situation of distrust for the tests that developers don't actually use them to improve their workflow. And then the kind of final code smell is kind of like a social one, where if you look out at your colleagues and all of your projects, and if you have a project that no one in your team wants to actually touch, kind of ever, but there's no real good way to explain that itself is a code smell, even if there's not something specific about it, just people avoid it. The beginning of technical debt, in a lot of ways, is not knowing how to say no to features, right? When you receive requests for hundreds and hundreds of features and you want to get them implemented as quickly as possible, you take shortcuts to make that happen. And sometimes the features don't even make sense to begin with as a part of that project, but you want to make your customers, your fellow hackers happy, and so you do it. You think, I'll take the shortcut and clean up the mess tomorrow. And when the priority becomes pushing code over having good design and reusability, which is totally understandable, right? Because we all want to be seen as good, productive hackers. We want to push a lot of code, but that we can get in our own way with that. So that's the beginning of technical debt. The end, like I was saying, is at the end of the dev cycle, we have one more fragile thing in production. Even worse, future dev cycles and deployments take longer and involve more fear and uncertainty about what we're going to do. We find ourselves hesitating from actually deploying what could be a new simple feature when it has all this other cruft around it. And the effect of this on the morale of the dev team is what you really want to avoid, right? Because we want to have happy, healthy dev teams that can actually function and do more work faster. But if you accumulate all this debt over time, you can have a culture of despair, a culture of cynicism on your team, and those are things that ultimately undermine your entire project, your entire effort. So some numbers on technical debt in our project, and really just one number is lead time, which in the DevOps world is typically measured as the time between when a commit is committed that fixes a bug or introduces a new feature, the time between that and when it is deployed in production. So for our services, we can't actually measure that because we don't have an automated deployment system, so there's no way to map those two together, but we can get close to it by measuring the time in our Git commit history between when features are committed and when the release is cut that includes that. So ideally, you want that time to be as small as possible because as soon as you make a change, you want to get it in production to be able to ensure that it works the way that you think it does. If a tremendous amount of time goes by in between those two events, then you wind up in a situation where when you go to deploy, it contains changes that haven't really been tested in the real world, and they were written so long ago that you don't remember anything about them or what they were, any caveats that might be there, and so then you break production and things catch on fire. So here's just some repositories that were on my machine, calculating the lead time as modified for us with them. And you see like projects at the top that are very popular and being worked on actively, things like Pagger and Moat, have on average a 2-day lead time, which means if a feature is committed, 2 days later it's in production on average, which means that quite often it's actually faster than that. Things are fixed and then they're in production the same day. And you see a variety of other projects. This is not a variety of other projects that are in the good camp on this. And then you get into the bad ones. And they're not the ugly ones, they're just the bad ones in the middle. And you see some of our projects that are larger in scope and have more complexity to them, things that have less developers focused directly on them. And then the ugly, these are the ones. Take a look at the bottom. Does anyone know Python Kitchen? One person. Maybe nobody knows any of these services. I should maybe explain more. Kitchen is not actually a service, it's just a Python library that provides a whole variety of utilities for general purpose programming in Python. And so it's like everything but the kitchen sink. It's kind of a catch-all bucket. So, I mean, the result of that is that it's this grab bag of you don't even know what's in it, and if you change something in it, what is that going to break? You have no idea, because it's like a totally unstructured mess of things. So on average, it takes 181 days for a commit to make it in a release in Python Kitchen, which is a really long time. I have highlighted in bold up there things like Nuancia. That is our web application for voting, collecting votes from the community on supplemental wallpapers for Fedora. And so the lead time there of 52 days actually makes a lot of sense because we only hold elections every so often on intervals. So typically we'll have an election, find some bugs, fix the changes then, but then we'll forget to deploy them until the next election comes along. So it has a pretty regular, even lead time there. So what do we do about this? There are cultural practices for dealing with technical debt, and we all kind of know them. They're just good dev practices, right? So don't let these things happen. Just be a good coder all the time. There's the Boy Scout rule. The Boy Scouts of America have this rule that if you go to a campsite, you need to leave it cleaner than it was when you got there. Do the same thing with code. When you check in a patch, you should also fix any kind of cruft around at the same time. But this only goes so far because we're under a lot of stress and a lot of pressure to produce code faster. You can have institutions like code review. I mean, everybody should be doing code review these days. No features without a test. That's kind of a given. It's elementary in software development these days. And we've recently started experimenting on my team with instituting week-long or multi-day-long periods where we all take a break from working on other aspects of our projects and then instead just focus on dealing directly with technical debt. And we'll see how that plays out in time as we do it again and again. So those are cultural practices, and this kind of gets to the core of what I want to talk about is architectural practices and how can we design our systems in a bigger way to help reduce, hopefully, the tendency to introduce technical debt into our projects in the first place. So microservices is the very, very popular topic these days. Something to think about. If you look at I don't have a graph of it, but the Google search hits results for it just begin to go up really fast in 2014. In 2015, it's through the roof. I mean, it's just astronomical. It is sometimes up for debate, or it's confusing. What is the difference between service-oriented architecture, which is an old term, over a decade old now, and microservices? And it's not clear that there really is any fundamental difference between the two. It's really just kind of a restatement and refocusing of the service-oriented architecture literature. into this microservices thing. And it sounds good, right? Micro, very good. So some characteristics of microservices. What it boils down to is just componentization of your software into services. Componentization is the name of the game in software generally, right? When you write your first program when you're in the 6th grade, it's this really, really big, long script that just goes through and does one thing after another. And eventually it gets so long that you realize you need to organize it into functions. And then as you write more complex software, you have to organize those functions into classes, and then those into modules, and so on. So this is just yet another degree or layer of componentization, but typically along the line of a network service or a network boundary. The literature talks about organizing microservices specifically around business capabilities. So that's how you try and figure out what should be a microservice and what shouldn't be. A case for like an enterprise example would be payroll, right? Like payroll serves a specific business capability in your organization, and so building a service to represent payroll would be one way to do that. Another aspect is smart endpoints and dumb pipes, which is something that I hadn't really encountered until I started doing research for this talk. But the idea here is that you have really, really intelligent services and clients, but the mesh that connects them, whether that's HTTP and REST or a message bus or something like that, should be really, really dumb. So the counterexample to this is the ESB, the Enterprise Service Bus, or the egregious spaghetti box, right? Which you have all these services, and they get connected to one another, but none of the services are in control of who they can talk to and what kind of data they consume. Instead, there's this box in the middle, the ESB, which has to be administered and defines all the routing and mapping and the queues between all of these different aspects. So that tends to be a single point of failure technically, in that if it goes down, everything else is down. But it's also a single point of failure socially, because in order to get any sort of change done, you have to go to committee and get people to agree to add certain rules to your ESB box to do what it needs to do. In contrast, think of the internet, where you have smart servers, HTTP servers, sorry, the web, World Wide Web. You have smart HTTP servers and smart browsers, but the connection between them is a really, really dumb thing. You can go and request any website that you want. I mean, it's like absurd to think of any other way of doing it. Other ideas like decentralized government, which has like this political twist, but it's more about how you organize your projects. Decentralized data management. In this case, Amazon had this famous rule, right, that no two services should share access to the same database directly, that every database needs to have a service in front of it with an HTTP interface that you then interact through. And if you've ever worked on a project where there were, or a couple projects where things shared read and write access to the same database, you know that it turns into a horrible, horrible mess down the road where, again, you change one, you have no idea if it's going to break the other, et cetera. A requirement, if you begin getting into microservices, is infrastructure automation. And this just means if you're going to be deploying more services, then you need to have some sort of way to automate the deployment of them. Otherwise, you burn way more time doing that. And then designing for failure, right? If all of your services are now distributed in that they rely on a network boundary to communicate with one another, that can fail, and it will fail. So your services can no longer expect that the function that they used to call will return with no problem, but instead they have to expect that it may not return at all, or it may time out. It may fail in ways that weren't expected. So graceful degradation is the name of the game there. And evolutionary design, right? I mean, designing like an entire suite of microservices up front is one thing, but if you have them already split in the first place, then you can add them incrementally and change your entire architecture that way. So how big is a microservice? It's not it's not clear. There's a lot of disagreement about it. So one, and this is the one that I like the most, is that if you can describe the service with one responsibility, that it's responsible for one data asset or one type of data asset, that's a good limitation to put on it. Other people argue that it's primarily about like developer cognitive resources. So if the developer can't rewrite it from scratch in 2 weeks, then it's too big. Or if the developer can't hold it in their head all at one time while thinking on it, then it's too big. But those are maybe flaky or fluffy definitions. In contrast to monolithic architectures, right, where you have a handful of very, very large apps that do a lot of things themselves, when you scale out to having lots of microservices, you put this new kind of load on your operations team and the amount of deployment work that they have to do. So in order to deal with that and making sure that we don't have that pendulum that swings back and forth between dev and ops and each one of them pissing the other one off, on a month-to-month basis. There are different patterns and suggestions for how to deal with that within your organization. One is the you built it, you run it rule, which is that when you write a new service and you deploy it, you need to be responsible for the operations of that service, at least for a certain amount of time. And so Google does that, for instance, where the dev team has to operate the service for the first couple months of its existence, and then it goes over to an operations team that then works on it. But if the Nagios alerts go through such a threshold that that it's like a predefined threshold for when that happens, then the operations will hand it back to dev, and they then have to answer their Nagios calls in the middle of the night again for that. So ensures a certain degree of accountability. And another aspect too is that when you have all these variety of services, how do you make sure they're all actually working? So application telemetry and doing monitoring of the actual features in the application is really important as well. So Etsy does this, right, in that they have instrumentation on every single feature on every single app, not just at the infrastructure, but in the application itself. So every time someone clicks on the login page on Etsy, they have a graph in collect D for views of the login page, and then a separate graph for actual logins, so you can get the difference and see how many people see the login page and get confused, right? And walk away. LinkedIn does this to the max in that they actually log all of your keystrokes and mouse movements and how much time you spend on different sections of the page. Yeah, right. Oh. But that gives them crucial feedback that they can use to feedback into the development process. In terms of thinking of our applications in Fedora Infrastructure, if people know old PackageDB, it was a classic example of a monolith for us that we then split into a variety of services. It's PackageDB, and package is a really loose thing, so it has everything to do with all packages. Well, that's too big. What we've narrowed it down to now is that the PackageDB should be responsible only for ACLs. It's for who has access to packages and who does not. But it used to have this application data in there, which has since been split out into things like AppStream. And it used to have this mechanism to vote on packages and rate them and tag them and stuff. And we split that out into another service called Fedora Tagger. And as a result, we're able to iterate on PackageDB, which is a really critical system, much more quickly than we could otherwise. We have FAST. FAST similarly has a whole bunch of responsibilities for granting Koji certs and managing people's individual accounts. It used to also be the login mechanism for all of our other web applications. So we split that out into Epsilon and are using OpenID now, which decoupled those two. And Bodhi. How many people in the room know Bodhi? Have you used Bodhi? Cool, great. So Bodhi is this really another really important piece of our infrastructure, but think about the things that it's responsible for. It's the place that packagers go to submit a new update. It's the place that QA people come to give feedback on updates. It's the place that you go to manage build root overrides, which it's not clear that really has anything to do with updates at all. And then it's also baked in, especially in the old Bodhi one, baked into the same application is the release engineering process that actually produces the repos. There's so many things going on there that iterating on Bodhi, especially Bodhi 1, was really difficult. And Bodhi 2 is a lot more separated out and easier to hack on now. Say Koshi and the new PackageDB arrangement and FMN, all three of them I think are really good examples of peeling off the different responsibilities of services, peeling off the different responsibilities of a monolith into different services. And we're really happy with the way those are working. Like Koshi is composed of 4 different services that all have different things that they're responsible for in the process of doing that continuous integration. So if we want, so we're headed down this path already of doing a microservices split up in Fedora Infrastructure, and we're like well on our way through it. But if we want to take it further, I think there's some prerequisites that we would need to meet. We're well on our way on some of them and not very well on our way on some others. The first being automated tests. We have them, almost all of our applications have them, some of the older ones don't. But there is a limitation, there are limits to what we're doing now, and we can maybe think outside the box and go to some bigger scale testing ideas for our apps. Without automated tests, you have no idea if you're going to break production when you push these things as fast as you want to be pushing them. Rapid provisioning of new hosts for new services is something that we actually don't have at all. It's really difficult right now to provision a new service in Fedora Infrastructure, and it's probably our biggest pain point. And I mentioned in a talk earlier today that a side effect of that is that it encourages our developers to bolt on functionality to existing apps instead of saying, oh, this clearly needs to be its own thing. Except once they write the app, there's then like a week to 2 week wait period while we actually just set up hosts and basic infrastructure for it. So that's something we can get a lot better at, I think. Against provisioning, rapid application deployment, we're actually pretty good at that right now. We have fully automated playbooks for maybe half of our applications that with one run of a playbook, it does all the things that need to happen to upgrade the service from an old version to a new version, which includes like taking it out of the proxies, taking it out of Nagios, updating a front end and a back end, shutting them both down, doing a database upgrade, starting everything up in the opposite order. So that is now like a flick of the wrist, and it's really nice to have, and it's facilitated more development. Monitoring, again, we have that, but it's not automatic yet, so we have to remember to add things to Nagios when we deploy new services, and we've forgotten to do that, I mean, more than once. So that's one of the things you just need to be automatic so you can move without fear. And a DevOps culture is something that I think our team has had from the beginning, just in that we have a really organic relationship between our dev team and our ops team, where we hang out in the same places in IRC, we're basically the same people, we hand information back and forth, and we also have an organic relationship with our customer, right? If we have a customer, the customer is the Fedora community, right? So we are packagers ourselves, so we get to feel the pain point and have really feel the pain points of our own apps, and then know what bugs we need to fix to be able to move forward. So without that, you can get into a lot of trouble and mess with miscommunication. Of all those things we can talk more about and dive more into, I want to focus just on testing, kind of for the rest of the talk. So that, I mean, there's different strategies for testing, right? And so here are 4, there are more. But we do really well component testing, the first, and end-to-end testing, the last. For end-to-end testing, we have a tool called Rube, which is really just a thin wrapper over Selenium that steps through our entire staging infrastructure and logs into services and tries to post a Bodhi comment and does all kinds of things. But it takes a really long time to run, just because it takes a long time to run through all that. So it is cool in that we're sure that all of staging is working, but it's a huge limitation because as you're making changes, you can't just run Rube and then know right away what's wrong and fix it. You're waiting for a half an hour for the thing to complete. On component testing, I mean, that's like what people call unit testing. We actually don't do any unit testing of specific functions, but we do tests of our whole components, like what you might call a functional test, that an HTTP call will return this kind of data and things like that. In the middle, integration testing and contract testing, we actually don't do any of that right now, but I'll talk some about possibilities for that. So contract-based testing, has anybody heard of contract-based testing? One name, we talked about it earlier. Great. So some people know, this just blew my mind. I think it's the coolest idea. The idea is, well, so start off, that we have services, right? Service A, under the hood, talks to service B when a request comes into it and then returns data which then comes back to the client. That happens. So when we're running a test on our system, we don't want to actually have to make a call out to service B, either because we're in a test environment and it doesn't exist, or if we could stand it up, it's going to take a long time to do that interaction, and we want our tests to run fast. So what we do, the standard practice, is to mock that request, and that involves building a kind of fake code object that returns fake data, but then you can test the path in your own component, your own service, and move along. But it generates, just go back. This just generates new problems, right? Because over time, service B's own API changes, right? It's being actively developed, and if its API changes, that thing that you mocked out, you said it was going to return this data, but the service really doesn't return that data anymore. So your tests are still passing, even though when you push to production, you're going to break, and you don't know. This is called fragile mocks or brittle mocks, and it is totally our problem. I mean, we have it in every one of our applications. We have to, it's not that the tests are worthless, but we just have to be hyper aware of what mocks we need to change when we change another service. So that introduces a lot of lag and pain for us. So the gist with contract-based testing is to just take a step back and realize that service B, the thing that you're depending on, it also has its own test suite. And you have put a lot of work into that test suite to make sure that it tests all the interfaces and does what you think it should do. Those tests are written in some code, and they can't be automatically pulled out this way, but they boil down to saying, service B saying, when I am called this way, I'm going to return this kind of data. And when I'm called this way, I'm going to return this kind of data. Assert that to make sure that's true. If you could take that data in that test and extract it out, you can actually do some really useful things with that. So that's the idea with contract-based testing. You take what was the test of service B and ship it as a library that is then used as a mock for service A and everything else that depends on service B too. So that when you change service B, you presumably change the tests, right, to make sure that the new functionality is working how you want. You then distribute that library and notice that, oh, all your tests failed in service A, and you can fix that before it even gets to any further environment. And this extends beyond just 2 services in isolation, right? Like a whole chain of things. You can figure out all sorts of problems about them with this strategy. For the other testing strategy, so that was contract-based testing. For integration testing, I saw a talk the other day by the JBoss developers talking about Archillion Cube. Anybody know Archillion? One hand? it was really cool, right? So it's in the Java world, so we typically, don't trade technologies back and forth unless we go researching for them and looking for them. But I was kind of blown away. It's a platform and a framework to use in your tests to start up the services that are under test and their dependencies inside containers, which is cool on its own. So you can actually do a full integration test on your own box of service A and service B. You have a kind of YAML definition that describes here are the other service relationships, so start up these other containers, and you can test them kind of end-to-end on your own box relatively quickly, right? It's slower than contract-based testing or component testing because you have to actually make the database call to the database and actually return it, but it's faster than end-to-end testing for sure. The really cool thing that they did, they have this Archillian cube, cube.q, the letter Q, and what it does is it then introspects all of your containers to find all of the ports that they've exposed to one another, and it inserts TCP proxies between all of them. So then in your test, you can write like with a context manager decorator, say in this test, do the interaction that you did before, but make the TCP connection close prematurely, or slow it down to the rate of like a dial-up modem, or make it do a slow close or things like that, so you can simulate all kinds of network failures and test things that you could never test before. We can't even test that in our staging infrastructure now. It's a whole new ballgame. So from testing, the kind of last thing I'll touch on is like for Fedora, what would a continuous deployment toolchain look like for us? And this is just a proposal, right? It's not something that we'll necessarily actually do, but it's kind of cobbling together the pieces that we do have that are already relatively mature, and just with a little bit of glue, we can get very close. So we have Git repos both on GitHub and on Pagure. We have a Jenkins instance, but we would have to really beef it up, I think, to do this, because we would need to make sure that all those tests run in a trusted environment and make sure they pass before we move forwards. We would need, in this instance at least, is thinking about using Copper as the place where we would actually build the RPMs to deploy to our systems, which is what we do. But we would need a policy change, right? Currently, we have to have everything that we deploy is in Fedora or EPEL, but Copper is not in that subset, right? So we would need to revise our rules to do that. We would then need some sort of system that would just map our Git repositories to the playbooks that do the updates, which would be a very, very small piece of Python code, I think, to write. And then we would just have to make sure that all those upgrade playbooks I was talking about, we actually have a full suite of them, because right now we only have half our services are automatically upgradable. And then very, very last, we would have an arithmetic amount of work to get all of our services ready to do this in Git and in Jenkins and in Ansible. And that is not an exponential amount of work. It's accomplishable, something we could do in a year. But yeah, so that we could do that. So the question is maybe why bother, right? So like there's all this hype about microservices. We have this huge astronomical graph of searches on Google. But we have to do a lot of stuff to be able to get there. We have to have new test frameworks and this contract-based thing and the container thing, and then we have to have new playbooks, and we got to set up Jenkins, and it's like not just do it on a whim. So what problems do microservices actually solve for us? One of the big answers is that they are web scale, right? But that's not necessarily a problem for us, right? We don't have any kind of traffic that's coming at us like one of the major infrastructure sites on the web. If you have a monolith and you need to add more capacity, you have to duplicate the whole monolith along extra app nodes. But if you have microservices, you can just scale the ones that are under heavy load. But again, that's not really our problem. A problem that it may help solve for us if we carry it out to its full conclusion is just scaling the ability of our developers to reason about the code that they're changing and move faster in that direction. And that's the thing that I think we really want to focus on. Bodhi being like the big counter example of it taking so long to get to a version 2 rewrite because it involves so many things to think about. A last slide on complexity. By doing microservices, we're going to get stronger boundaries between our systems and less kind of bleeding of functionality and implementation between them. Simpler subsystems, they'll be independent of one another, so we can change them and take them down without that much coordination or worry. And we have an opportunity here to get into some technological diversity that we've never been able to do before. We have a rule of only Python in our infrastructure, which is not because we're like Python chauvinists, but is just because we only have a few developers, right? And if we start introducing Erlang and Scala and Go and all these other things, not all of us are necessarily proficient in those languages to be able to fix any problem. So, but with microservices, we have an opportunity to do that where we didn't before, when things were more tightly coupled. Let's say lastly, there's this initial investment, right, in code complexity, right? When you are writing a monolith from the get-go, you can write the whole thing and put it together. But with microservices, you now have to start with these test frameworks that mock out other subsystems that maybe don't even exist yet. And so that's a cost you have to pay. But the idea is that over time, the amount of maintenance work that you have to perform to put into these systems goes, it doesn't, what am I trying to say? The amount of maintenance work doesn't necessarily go down, but it doesn't escalate in the way that it does with giant monolith systems. So yeah, that is all I have. If people have questions, I'd love to answer them. Wow, I saw a couple. I'll start with you.
Is this kind of architecture suitable for other than build it under the deploy kind of projects?
You mean like desktop?
Myself, I'm a QA. If this would be used in a small team of people who work on testing something that isn't currently your microservice, we are in a hybrid for PIPA, if you know the project.
Yes.
And we have a lot of technical debt in our upstream QE, and I'd like to introduce some new tooling. Is this suitable for us? And is it manageable in a small amount of people?
Yes, because we have a small amount of people. But that's the risk that you get to. I mean, we have maybe 4 full-time developers and 3 full-time sysadmins, but their responsibility is spread across maybe 40 or more services. And it's at the point for us where I think it would be, it is definitely risky to proceed much further down this road for us. But it's not clear yet whether it will be a good win or not. So, to repeat the question was, is this a suitable, is this architecture suitable for application to small teams? Correct. Other questions? Dennis?
Data question. So when you split the package DB up into multiple services, each of the services now has a concept of a package name, for example. What happens if in package DB you rename a package? How does that data get reflected in other services? We don't have the referential integrity. They might have the same application.
Right, right. So in that situation, we just don't allow changing of things that you might refer to as a primary key. So we're not allowed to rename things in package DB.
Primary key is kind of something you do up front when you're designing microservices.
Yeah, and it's tough to know what you'll need at that point. We definitely didn't think that through that explicitly. I think there was just an assumption that the package name is the package name. And if you were to rename it, you would instead be deleting one and creating a new one. And if you really cared about the data, then you would have to manually script a migration in the dependent services. Yes, Mike?
I'm just wondering how this idea of microservices meshes with the rapid application deployment. Because every time you create a service or break out something from another service, you're creating more integration points. And so every time you release, you potentially break dependencies of that service. And I know the answer is generally integration testing, automated integration testing.
Yeah.
But as you get to more and more services, is that really realistic to expect that combinatorial testing problem to be manageable?
So that also is then the pain point that we're hitting right now, where the number of interactions is, while not exponential, it's very large. And we haven't embarked down the road yet to figure out if it will work in practice, but I think contract-based testing is really going to be the savior there. If I could jump back to the slide.
I have another question about that one.
Yeah. Oh, where did it go? There it is. There's 2 models for how to carry this out too. There's consumer-driven contract tests and producer-driven contract tests. And what I described was a producer-driven contract test where service B is the thing providing the service kind of at the end of the day. And so we use its tests as the mock and push things kind of socially in that direction. But the one that actually looks to be most prominent in the literature is consumer-driven contract testing, where you make service A write its expectations in some format, and then you submit those to service B, and service B is expected to include all of its many consumers' contract expectations in its test suite. So then you know in service B that if you ever make a change, you know which service it's going to break because you're running their tests. You're running yourself against their expectations. Does that make sense?
Right, but I think that exacerbates the combinatorial problem, right? Where now you have to push the expectations of a single new service into every other service that it interacts with. And
I agree.
It seems like a really crazy management problem, even ignoring the social aspect of communicating with however many upstream.
Yeah, I agree, and that's why I'm leaning towards the producer-driven one, where we take our most dependent on service and begin working on it, and then we can later then enable its dependent services to pull in its contract.
Does that become a problem if your services are
It could, so you would have to write the framework that performs this in some sort of language agnostic way. For instance, there's, I know of 3 implementations that do this. There's one in Java, and I think there's 2 different ones in Ruby. I haven't found a Python one yet, but they all of them share the capacity that they can work by integrating directly with the process that's being tested, right? If it's in Ruby, it can attach to the Ruby test suite and just do it right there. But for everything else, it has a standalone server mode where you'd stand it up just as a separate process on the box, and then you actually make HTTP requests to it, and all it does is read a YAML file and return the expected response, or a 404 or a
So the contracts wouldn't necessarily be libraryized, they would be in some...
I use the word library, but yeah, it could be in some independent format, and probably should be. For us, we could get away with doing it as a library simply because we're already a mono language in Python, but that was perhaps unwise to start there. Cool, no problem. Yes?
Okay, that's not exactly a question, but since you have had the question on the contract testing and on the contract testing, what we've been doing is an open source project that allows you to create consumer-driven contracts and test them at the same time.
Oh.
So the tests are generated automatically, and you should not, if you set it up right, you should not be able to deploy the new version of your application unless you have a working version of stubs. So the automatically generated stubs, also apart from them, there were automatically generated tests that check if the stubs really work as the server works, and only unless these tests have passed can you deploy this. But this is mostly for JVM as it's written as a Gradle plugin. We won't make it for Maven, but maybe you can see it and adjust it to your tech stack. Yeah?
I would be curious to look at it and analyze it, but we don't have any Java or Maven or Gradle anywhere in our pipeline right now, so it would be a big hurdle for us to implement, but I'd love to look at it.
In the JVM mode, there are some attempts. This is one of them, and I think if you want to do the microservices, if it's useful for you, you can try making it for Python. And I don't know Python ecosystem really what tools you use for building, but make that be useful.
Yeah, thank you. Yes, Luboš?
Yeah, I have a question with the semantic Linux. Like, when you are breaking some of the Fedora services into different microservices, have you run into a situation where you need to reference an object in some other service and the primary key or something is not actually some nice name? For example, for users, you can use like usernames. For packages, you have names. When you run into a situation where you need to reference something that just doesn't have this name,
Yes.
you need to use some other way.
Yes, we take that on a case-by-case basis. We don't have a general solution. Bodhi is a good example. How do you refer to an update? You can refer to it as the comma delimited set of all the builds that are in it, but that can change. And then there's the Fedora update ID, but there's this big kind of cryptic string that is the update ID. But it used to be that was not set initially at update creation, only later once it made it into a push. So there was this period of time where there was no key there. And we resolved that by assigning that alias, the cryptic string, at the very beginning at creation, and then ensuring that never changed. So, but that's a case-by-case basis, I think. Steno?
I wonder if, because it's been mentioned, right, there's a lot of innovation going on in different parts of the open source ecosystem, and big chunks of it are not Python.
Yes.
And big chunk of innovation is done in Java world. I wonder if there's opportunity for us to, even if we don't directly use what they implemented, either re-implement things that are kind of neat ideas ourselves, or just learn basically from other communities what they've been able to do as taking their ideas.
Yeah.
I'm not sure if there's a question. Have you thought of reaching out maybe to Java folks or getting their ideas of how things could be done?
Yeah, I tried this weekend. So yes, that's good. We should do more of that. And there's not enough of that for sure. So. Other questions? In the back? Oh, I'm sorry, we're out of time. If you want to ask a question, we can talk up front. So thank you very much.
Those who ask questions, please go and grab your scarves. You deserved it.
Oh, yes, right. I didn't do my job. I said I would do it.
I have a scarf.
You can have 2. Price of 1.
It's not that cool.
Yeah.
I had a question about, so you said the Koshi is actually 4 services of it?
Yeah.
So in practice, are those like developed together, or they're just kind of very like I wonder how independent are microservices when it comes to like from a development perspective.
Yeah, yeah. Again, it's case-by-case basis, right? But like Koshi was developed with all four from the outset. They like foresaw it and just designed it, and that is rare, I think. Typically, you start with things as one service. They recommend that you build a monolith first so you understand what your problems will be, and after that is when you start peeling it. But you try and go into it with an expectation of trying to keep things clean. Certainly in Fedora, we didn't have that in the beginning. We had a lot of monoliths staggering around. So.
Those four services actually have like their own cycles and
Yeah.
independent things.
Yeah, they're all in the same Git repo, so they all have the same README, but they're like all kind of part of the same thing. And the thing about they work with Koji, as if Koji is just yet another microservice. And Koji too is composed of KojiD, the Koji Hub, Kojira. I mean, kind of.
It wasn't for that hub thing that has like
everything else in it. I know.
100,000 lines.
Yeah. Hey, oh, thank you. Yeah, no problem.
I was just like wanted to ask quickly, talking about not some combinatorial kind of like products, but just from a developer perspective. I'm a TDD guy, but still I'm kind of missing like the monolith perspective, kind of like the stack down, just like organic testing, as you said, like integration wise, right? Should I just like forget about it? It's like it seems kind of related to how I felt about just like getting rid of my object-oriented programming mindset now, embracing more the functional side.
Yeah, me too.
Maybe am I just like
Yeah, we have a handheld.
completely on the wrong track still?
Yeah.
Just like should I just embrace it? Like okay, breathe and let it go, and just like go for the as you said, like contract-based testing stuff? Or would you think like it just has shifted to, for example, a staging environment, where in the end you just still log on there and
do the end-to-end test.
click through and test everything? Would that be?
Yeah. Well, so I mean, we had done that for a long time, and we're reaching the limits of it now. Where perhaps it's a oh, you have to move. Yes, of course. Yeah.
Obviously, it depends on the complexity, right?